Derive the expression of the electric field intensity. Derive the expression of electric field intensity at the center of a uniformly charged semicircular arc of linear charge density lambda. At the center of a uniformly charged semicircular arc of linear charge density lambda. In the diagram MNB, a semicircular arc which is uniformly charged with a charge plus q. Lambda is the linear charge density of this semicircular arc. We can draw a horizontal diameter. Mn is the horizontal diameter of this semicircular arc. Mn is the diameter. We can denote the center of this semicircular arc. We can denote center. In this case, O is the center of the semicircular arc. Also, we can denote y and x axis, which are mutually perpendicular to each other at the center O of the semicircular arc. X-axis is along the diameter Mn and y-axis is perpendicular to the diameter Mn. R is the radius of this semicircular arc. We can extend the negative y-axis. We can denote negative y-axis, that is y prime. Negative y-axis y prime. AB is a small element on this semicircular arc. AB is a small portion of this semicircular arc, and the length of this elementary portion is dl. Length of this small portion of the semicircular arc AB is dl, and this small portion of the semicircular arc, that means the small portion AB, has the charge dq. dq is the charge of this small portion or small elementary portion AB of the semicircular arc Mn. And this small part or small portion AB subtends at an angle d theta at the center O of the semicircular arc. And here the small portion AB makes an angle d theta at the center O, or this small portion AB subtends at an angle d theta with the center O of the semicircular arc, and this small portion AB has the charge dq. We can place unit positive charge, +1 charge at the center O, and field intensity at the point O due to the small portion AB is dE. Along this direction, along the direction OZ1, field intensity dEx, which is due to the small elementary portion AB of the arc. We can denote a point P. At the point P, theta equal to 0 degree. At the point N, at the point P, theta equal 0 degree. Now here at the point P, theta equal 0 degree, and the angle subtended by the small portion AB is d theta at the center O, and obviously this small portion AB is at an angle theta with y-axis. Theta is angle, and also field intensity dE at the point P acts at an angle theta with the negative y-axis. And this field intensity dE is resolved into two rectangular components. along negative y-axis and negative x-axis. Here dE cos theta is the rectangular component of the electric field intensity dE at the point O, and this rectangular component dE cos theta acts along negative y-axis, that means vertically downwards, and the other rectangular component is dE sin theta of the electric field intensity dE at the point O due to the small element AB, and which acts along the radius along OM. And we can consider another small part CD on the semicircular arc, and this small part CD has the charge dq and length is also dl. dl is the length of the small part CD, and this small portion CD subtends at an angle d theta at the center O of the semicircular arc. The small portion CD on the arc makes an angle d theta at the center O, and the electric field intensity at the point O, or that means at the center O of the semicircular arc due to the small portion CD is dE, and this electric field intensity dE at the point O acts along OZ2, and this field intensity dE due to small part CD is resolved into two rectangular components, and if this angle POC is theta, in that case angle y prime O Z2 is also theta, that is vertically opposite angle, and the electric field intensity dE along OZ is resolved into two rectangular components. The rectangular component which is acting along negative y-axis is dE cos theta of the electric field intensity dE due to the small part CD, and the electric field intensity dE which is acting along OZ is resolved into another component, that is dE sin theta, which acts horizontally along the radius ON. That means this rectangular component dE sin theta acts along positive x-axis. Let Mn be a semicircular arc of radius r, not A, of radius r, which is uniformly charged with a charge plus q, dl be the length of the small portion or the small elementary portion AB of the semicircular arc, subtending at an angle d theta, at the center O of the semicircular arc. dl be the length of the small portion AB of the arc subtending at an angle d theta at the center of the semicircular arc. We can consider the semicircular arc. Mn is the semicircular arc which is uniformly charged with a charge q. So this semicircular arc is uniformly charged with a positive charge plus q, and we consider the center O. O is the center of this semicircular arc, and the small part or small portion AB of length dl and charge dq subtends at an angle d theta. This small portion AB makes an angle d theta at the center O, and this small portion AB has the charge dq, and unit positive charge plus 1 charge is placed at the center O. Field intensity at the point O we can denote y-axis and positive x-axis. and also we can denote negative y-axis. Field intensity at O due to the small part AB is dE. This field intensity dE at the point O acts at an angle theta with the negative y-axis. Acts at an angle theta with the negative y-axis. So this angle will be again theta. Due to dq be the charge of the small portion AB, and this charge dq of the small part AB applies an electrostatic force dE on unit positive charge at the point O. The electric field intensity at the center O of the arc of the semicircular arc MN due to this small portion AB of the semicircular arc of charge dq is given by dE equal 1 by 4 pi epsilon 0 dq divided by r square, where r is the radius of the semicircular arc. dE equal, and in the diagram r is the radius of the semicircular arc, and dE equal 1 by 4 pi epsilon 0 dq by r square, which acts along OZ1 direction. Along the direction OZ1, dE is the electric field intensity which acts along OZ1 at the point O, and which acts along OZ1 at an angle theta with negative y-axis. The small portion AB has the charge dq, and field intensity at the point O due to the small portion AB is dE. dE is the field intensity at the point O due to the small portion AB, and this field intensity dE acts along OZ1, and which acts at an angle theta with the negative y-axis or with y prime axis. Similarly, the electric field intensity at the center O of the arc MN due to another small portion CD of the semicircular arc of same length dl and charge dq. Another small portion CD of same length dl and charge dq is given by dE equal 1 by 4 pi epsilon 0 dq by r square, which acts along the direction OZ2 at an angle theta, at the same angle theta with the negative y-axis. Now the small portion CD of the semicircular arc, of length dl and charge dq applies an electrostatic force. The small portion CD applies an electrostatic force on unit positive charge, and that force is dE. So dE field intensity acts at an angle theta with the negative y-axis. The rectangular components, that is dEsinθ, dot of the electric field intensity dE, of the electric field intensity dE, of the electric field intensities dE, due to all such small portions AB, CD, of the semicircular arc. The rectangular components dEsinθ, dEsinθ, of the field intensities dE, due to all such small portions AB, CD, of semicircular arc cancel each other's effect. the rectangular component acting along the diameter mn, that is dEsinθ, acts towards left, and another rectangular component dEsinθ due to the small portion CD which is acting along the same diameter mn towards right, that is dEsinθ and dEsinθ act in the opposite direction, and they cancel out each other's effect. That means this dEsinθ acting towards right cancel the effect of another dEsinθ acting towards left. dEsinθ rectangular component cancel another dEsinθ acting in the opposite direction. Cancel another dEsinθ in the opposite direction. Therefore, the effective electric field intensity at the center O of the semicircular arc Mn, which is the resultant of the rectangular components dEcosθ, dEcosθ acting along negative y-axis, dEcosθ, the rectangular components which is the resultant of the rectangular components, that is dEcosθ, dEcosθ, ... due to a number of small portion on the semicircular arc is given by E equal integration dEcosθ, and limits should be from minus pi by 2 to plus pi by 2. In the diagram, at the point P, theta equals 0 degree. At the point N on positive y-axis, theta equal to 90 degree or plus pi by 2, and if we rotate anti-clockwise, in that case at the point M, theta equal to minus pi by 2. Now, dE was the expression of electric field intensity due to a small portion. dE was 1 by 4 pi epsilon 0 dq by r square. dE equal 1 by 4 pi epsilon 0 dq by r square, where the linear charge density of the semicircular arc is given by lambda equal dq by dl divided by total charge q by pi a, where pi a is the length of the semicircular arc. In the diagram, dq be the charge of the small portion AB, and dl is the length of this small portion. In this case, linear charge density of the small portion AB is dq by dl, and if we consider the total semicircular arc, length of the semicircular arc is pi a, that's why lambda equal to q by pi a. Or dE equal 1 by 4 pi epsilon 0 lambda dl divided by r square, where dq equal to lambda dl. dq is the charge of the small portion AB. Or dE equal 1 by 4 pi epsilon 0 lambda r d theta divided by r square. Since d theta angle equal length of arc divided by radius, that is d theta equal dl by r. In this case, in the diagram, the small angle d theta is equal to length of arc, that is dl, divided by radius, that is r. d theta equal dl by r. Therefore, dE equal 1 by 4 pi epsilon 0 lambda d theta by r. dE equal 1 by 4 pi epsilon 0 lambda d theta divided by r. Therefore, E was integration minus pi by 2 to plus pi by 2 dE cos theta equal minus pi by integration minus pi by 2 to plus pi by 2 1 by 4 pi epsilon 0 lambda d theta r into cos theta. At the point P, theta equal to 0 degree. At the point A, n theta equal to plus pi by 2, and at the point M, theta equal to minus pi by 2. So at the point P on y-axis theta was 0 degree now, equal 1 by 4 pi epsilon 0 lambda by r integration minus pi by 2 to plus pi by 2 cos theta d theta equal 1 by 4 pi epsilon 0 lambda by r. Integration cos theta d theta becomes sin theta under third bracket minus pi by 2 to plus pi by 2 minus pi by 2 to plus pi by 2 equal 1 by 4 pi epsilon 0 lambda divided by r sin pi by 2 minus sin under bracket minus pi by 2 equal 1 by 4 pi epsilon 0 lambda by r sin pi by 2 is 1. Here what again we can write sin pi by 2 plus sin pi by 2 because sin minus pi by 2 is minus sin pi by 2 equal 1 by 4 pi epsilon 0 lambda by r 1 plus 1. Therefore, we get E equal 1 by 4 pi epsilon 0 2 lambda by r. E equal 1 by 4 pi epsilon 0 2 lambda by r. This is the expression of electric field intensity at the center O of a semicircular arc. Therefore, E equal lambda divided by 2 pi epsilon naught r. E equal lambda divided by 2 pi epsilon naught r. In the diagram, we have a semicircular arc which is uniformly charged with a charge q. Mn is the diameter of the semicircular arc. O is the center of this semicircular arc. We can denote y-axis and x-axis, and also we can denote negative y-axis, that is y prime. At the center O, resultant field intensity E equal lambda by 2 pi epsilon naught r, which acts radially outwards, which acts vertically downwards with respect to this type of semicircular arc, and E equal lambda divided by 2 pi epsilon naught r, which is the electric field intensity at the center O, of the uniformly charged semicircular arc. E equal lambda by 2 pi epsilon naught r, which is the electric field intensity at the center O of the uniformly charged semicircular arc Mn, and it acts radially outwards. It acts radially outwards along OY prime as according to the diagram, that is along negative y axis. So we get E equal lambda divided by 2 pi epsilon naught r.